In April of 2019, astronomers released the first real photograph ever taken of a black hole, closing a chapter of physics that had been quietly building for well over 2 centuries. Not an illustration, not an artist's concept, an actual image, assembled from data collected by telescopes scattered across the entire planet, showing a glowing ring of light wrapped around an absolute, impenetrable darkness, 55 million light-years away. That image was the ending of a story that started 236 years earlier, and it's a story with more genuine human drama in it than almost any other chapter in the history of physics. A career-ending public humiliation. Decades of open ridicule. A secret wartime calculation scribbled out by a soldier who died before he could see it published. And a scientific bet between 2 friends that took 16 years to resolve. This is the full story of how we went from a wild, speculative guess to an actual photograph. Let's start at the very beginning. In 1783, an English clergyman and geologist named John Michell was thinking through the implications of Isaac Newton's theory of gravity and light. Newton's physics implied that light itself, like any other object, should be affected by gravity. Michell reasoned that if a star were massive and dense enough, its gravity could theoretically be strong enough to pull light back in, preventing it from ever escaping the star's surface at all. He called the hypothetical result a dark star. It was a genuinely prescient idea, built entirely on paper, using nothing but Newtonian mechanics, more than a century before anyone had the physics to properly describe what such an object would actually look like. Michell wasn't alone in the idea for long. Roughly a decade later, in 1796, the French mathematician Pierre-Simon Laplace independently worked out essentially the same conclusion, describing what he called dark bodies in his own writings on celestial mechanics, massive enough that their own gravity would prevent light from ever leaving. Neither Michell's nor Laplace's version had anything close to a real physical theory behind it. No equations describing space-time. No way to say what such an object would actually behave like up close. It was speculative geometry, essentially a thought experiment about how far you could stretch Newton's rules before they implied something bizarre. Laplace himself later quietly dropped the idea from subsequent editions of his own work, apparently unconvinced it deserved to be taken seriously. Michell's idea was mostly forgotten for well over 100 years, a curious footnote rather than a serious research topic. The concept resurfaced properly in November of 1915, when Albert Einstein published his general theory of relativity, describing gravity not as a force, but as the curvature of space and time itself around mass. Einstein's equations were notoriously difficult to solve exactly, and Einstein himself assumed a full solution was likely years away. He was wrong by about a month. A German physicist and astronomer named Carl Schwarzschild found an exact solution to Einstein's equations within weeks of their publication, while serving on the Russian front during World War I, calculating artillery trajectories for the German army by day, and working through some of the most demanding mathematics in modern physics in his spare time. Schwarzschild's solution described the gravitational field around a perfectly spherical mass, and buried inside that solution was something strange, a specific radius around any given mass, now called the Schwarzschild radius, inside which the equations broke down entirely, producing mathematically infinite values. Schwarzschild sent his results to Einstein from the front lines. Einstein presented them to the Prussian Academy of Sciences on Schwarzschild's behalf. Tragically, Schwarzschild contracted a rare autoimmune skin disease while still serving at the front and died just a few months later in May of 1916, at only 42 years old, never getting the chance to see how significant his solution would eventually become. For years afterward, most physicists, including Einstein himself, treated the strange behavior at the Schwarzschild radius as a mathematical quirk, an artifact of an oversimplified model, rather than a description of anything that could physically exist in the real universe. The idea that a real, physical star could actually collapse down to that point seemed absurd. That assumption ran headfirst into one of the most brutal episodes in the history of astrophysics, and it started with a young Indian physicist named Subrahmanyan Chandrasekhar. In 1930, at just 19 years old, Chandrasekhar boarded a ship from India to England to begin his graduate studies. During that long voyage, working largely alone, he began calculating what should happen to a dying star once it exhausts its nuclear fuel. Conventional thinking at the time held that all stars, regardless of their mass, would eventually settle into a stable, cooling object called a white dwarf, held up against the crush of its own gravity by quantum mechanical pressure between tightly packed electrons, a phenomenon called electron degeneracy pressure. The idea, in simplified terms, was that quantum mechanics forbids electrons from being squeezed arbitrarily close together. So once a dying star's core contracted enough, that quantum resistance would kick in and halt the collapse permanently, no matter how much mass was pressing down on it. Chandrasekhar's innovation was combining that quantum mechanical picture with Einstein's special relativity, accounting for the fact that, as those electrons get squeezed harder, they start moving at speeds close to the speed of light, which changes how much resisting pressure they can actually generate. His calculations, refined over the following years, showed something different from the conventional picture. Above a specific mass threshold, roughly 1.4 times the mass of our Sun, now known as the Chandrasekhar limit, a dying star's gravity would be strong enough to overwhelm that electron pressure entirely, relativistic effects and all. There would be nothing left to stop the collapse. The star wouldn't settle into a stable white dwarf at all. It would keep collapsing indefinitely toward exactly the kind of object Schwarzschild's equations had hinted at nearly 2 decades earlier. Chandrasekhar presented these findings at a meeting of the Royal Astronomical Society in London in January of 1935. Sir Arthur Eddington, one of the most powerful and respected astrophysicists in the world at the time, a man whose own expedition had helped confirm Einstein's general relativity back in 1919, stood up immediately after Chandrasekhar's talk and publicly, dismissively tore the young scientist's work apart in front of the entire assembled scientific community. Eddington called the conclusion absurd, declared there should be a law of nature to prevent a star from behaving so ridiculously, and effectively used his own considerable authority to declare the idea scientifically unacceptable, without offering a genuinely rigorous mathematical counterargument of his own. The damage was immediate and long-lasting. Chandrasekhar was a young Indian scientist working in an overwhelmingly white, British-dominated scientific establishment, publicly humiliated by one of its most senior figures. Colleagues who privately agreed his mathematics was sound largely declined to defend him publicly, unwilling to challenge Eddington directly. Chandrasekhar eventually left England for the University of Chicago, and it would take nearly 5 decades and the accumulation of overwhelming independent evidence before the broader physics community fully accepted what he'd calculated correctly at just 19 years old aboard that ship. In 1983, Chandrasekhar was awarded the Nobel Prize in Physics, largely for exactly this work, decades after Eddington's public dismissal had first tried to bury it. The theoretical picture took another major step forward in 1939, just before the world's attention turned entirely toward war. American physicist J. Robert Oppenheimer, working with his student Hartland Snyder, published a paper describing in careful mathematical detail exactly what would happen if a sufficiently massive star collapsed under its own gravity. It would keep contracting, essentially forever, from the perspective of a distant observer, cutting itself off from the rest of the universe. What made the Oppenheimer-Snyder paper so significant wasn't just that it described collapse, but that it treated collapse as an inevitable, ordinary physical outcome, not some exotic edge case requiring special conditions. Take an ordinary, massive star, remove its ability to keep generating outward pressure through fusion, and gravity simply wins, following a specific, calculable, and completely unremarkable trajectory, straight toward exactly the kind of object Schwarzschild's mathematics had hinted at. It was a remarkably complete theoretical description of what we'd now call a black hole. The paper landed with almost no fanfare. It was published on September 1st, 1939, the exact same day Germany invaded Poland. Oppenheimer himself was pulled into wartime physics research and eventually the Manhattan Project. And gravitational collapse research was largely set aside by the broader physics community for the next 2 decades, overshadowed entirely by the war and its aftermath. The 1940s and much of the 1950s are sometimes called the dead years of general relativity research. The theory was seen by many physicists as a mathematically elegant but practically irrelevant curiosity, disconnected from the more immediately productive fields of nuclear and particle physics that had just helped win a war. The revival began in the early 1960s, and it started with a genuine observational mystery. In 1963, astronomer Martin Schmidt identified the true nature of a strange, compact radio source called 3C273. It was absurdly bright, outputting more energy than an entire galaxy of ordinary stars, from a region of space barely larger than our solar system, and it was billions of light years away. Objects like it were named quasars, and explaining how something so small could output so much energy pointed many physicists directly back toward Schwarzschild's old, largely ignored solution: matter spiraling into an extremely compact, extremely massive object could plausibly generate exactly that kind of energy through friction and gravitational heating, alone, without needing any exotic new physics. That same year, New Zealand mathematician Roy Kerr found a solution to Einstein's equations describing a rotating black hole, a far more realistic and general case than Schwarzschild's original non-rotating version, since virtually everything in the universe spins. And in 1967, physicist John Wheeler, during a conference presentation, used a punchy, memorable new term to describe these objects, replacing the clunky academic phrase, gravitationally, completely collapsed object. According to Wheeler's own later recollection, an audience member actually shouted out the suggestion during the talk itself, and Wheeler, recognizing immediately how much better it captured the concept, simply adopted it on the spot. He called them black holes. The name stuck immediately, and it did something the field badly needed. It made the concept vivid and intuitive enough for the general public, and for a new generation of physicists to actually get excited about. Around the same period, theorists converged on a strange and almost elegant conclusion about these objects, sometimes called the no-hair theorem. No matter how complicated or chaotic the star that originally collapsed to form a black hole, whatever wild magnetic fields, uneven lumps, or complex internal structure it once had, the resulting black hole itself can be completely described by just three numbers: its mass, its spin, and its electric charge. Every other detail about the star's original identity is, in a very real sense, erased. Two black holes with identical mass, spin, and charge are, as far as physics can tell, absolutely indistinguishable from one another, regardless of how differently they were made. It's one of the strangest and most elegant simplifications in all of physics. An object defined by a violent, complicated collapse that ends up describable with less information than a typical driver's license. The first serious observational candidate for an actual black hole came from a source called Cygnus X-1, a powerful X-ray emitter discovered in 1964. By the early 1970s, astronomers had determined it was part of a binary system, paired with a visible blue supergiant star, and the invisible companion pulling on that star gravitationally appeared to be far too massive to be a neutron star, the other known extremely dense stellar remnant. It was a strong candidate for the genuine article. In fact, the case became well known enough that in 1974, physicists Stephen Hawking and Kip Thorne made a friendly public wager over it. Hawking, with characteristic humor, bet against the existence of black holes, explaining afterward that it functioned as a kind of insurance policy. If he turned out to be wrong about black holes existing, at least he'd win the bet as a consolation prize. Thorne bet in favor. By 1990, accumulated observational evidence had grown strong enough that Hawking conceded, paying up on the wager exactly as agreed. Cygnus X-1 is now essentially universally accepted as a genuine stellar mass black hole. That same year as the original wager, 1974, Hawking made one of his most significant theoretical contributions to the field. Combining general relativity with quantum mechanics, he showed that black holes shouldn't be perfectly, eternally black, after all. The basic idea draws on a strange feature of quantum theory. Empty space is never truly empty, constantly producing fleeting pairs of particles and antiparticles that normally annihilate each other almost instantly. Right at a black hole's event horizon, Hawking argued, one particle of such a pair could occasionally fall in while its partner escaped outward. And to a distant observer, that steady trickle of escaping particles would look exactly like faint thermal radiation streaming away from the black hole itself. Due to quantum effects occurring right at the event horizon, black holes should very slowly emit that faint radiation, now called Hawking radiation, and over unimaginably long timescales, they should gradually lose mass and eventually evaporate entirely. For real astrophysical black holes, that evaporation process would take a timescale vastly longer than the current age of the universe, so it's never actually been directly observed. But the theoretical prediction opened up a genuinely difficult new problem, one that remains formally unresolved even today, known as the black hole information paradox. If a black hole eventually evaporates away completely, what happens to all the information about everything that ever fell into it? Quantum mechanics insists information can't simply be destroyed, that the universe should always, in principle, be reversible. Hawking's own original calculation suggested the radiation leaving a black hole would be purely random, carrying no trace whatsoever of what fell in, meaning that information really would be destroyed. That contradiction has driven a huge amount of theoretical physics research for the past 5 decades, and still doesn't have a fully agreed-upon resolution. While theorists wrestled with evaporation and information, observational astronomers were busy confirming something else entirely, that black holes aren't just rare stellar oddities, but sit at the very center of galaxies, including our own. Starting in the early 1990s, 2 independent research teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, began meticulously tracking the orbits of individual stars near the center of the Milky Way, in a region called Sagittarius A star. Over nearly 3 decades of painstaking observation, both teams watched those stars whip around an invisible central point at extraordinary speeds, tracing out orbits that could only be explained by an object with a mass of roughly 4 million suns, packed into a space smaller than our solar system. There was no plausible explanation other than a supermassive black hole. Genzel and Ghez shared half of the 2020 Nobel Prize in Physics for the discovery. By this point, astronomers had confirmed 2 very different populations of black holes, sitting at opposite extremes of a mass scale. Stellar mass black holes, formed from individual collapsing stars, typically weigh in somewhere between a few and a few dozen times the mass of our sun. And supermassive black holes, sitting at the centers of galaxies, weighing anywhere from hundreds of thousands to billions of solar masses. What was conspicuously missing for decades was anything in between. Intermediate mass black holes, theoretically weighing somewhere in the hundreds to hundreds of thousands of solar masses, were predicted to exist, potentially as a missing evolutionary link explaining how relatively modest stellar mass black holes could have grown over cosmic time into the monstrous supermassive ones seen at galactic centers. For a long time, solid observational evidence for this middle category remained frustratingly thin, a genuine gap in the black hole census that current research is still actively working to fill, including through some of the very gravitational wave detections mentioned earlier, several of which have revealed merger remnants sitting suggestively inside that intermediate range. The next major breakthrough came from an entirely different observational technique: gravitational waves, the ripples in space-time predicted by Einstein back in 1916. On September 14, 2015, the LIGO observatories detected the unmistakable signature of 2 black holes, each dozens of times the mass of our sun, spiraling into each other and merging into 1.3 billion light-years away, confirming not just that black holes existed, but that pairs of them could collide in exactly the way general relativity predicted. That detection, and the many additional black hole mergers LIGO and its partner observatories have detected since, is really its own complete story, one this channel has already covered in detail elsewhere. But it's worth noting here because of what it represented for this particular narrative: an entirely new, independent way of confirming black holes were real, arriving almost exactly a century after Schwarzschild first found them, hiding inside Einstein's equations. And then, finally, came the photograph. Beginning in April of 2017, a global collaboration called the Event Horizon Telescope linked together radio telescopes at observatories on multiple continents, effectively synchronizing them into a single virtual telescope, roughly the size of planet Earth itself, the only way to achieve the almost impossibly fine resolution needed to actually image something as small and distant as a black hole's silhouette. Achieving that synchronization required each individual telescope to record its data, alongside an extraordinarily precise atomic clock, accurate enough to align observations taken thousands of miles apart, down to a fraction of a billionth of a second. Over just a few days of observing, the global network recorded roughly 5 petabytes of raw data, so much that shipping physical hard drives by airplane between observatories turned out to be faster than transmitting it over the internet. Turning that mountain of raw data into an actual image required new computational techniques nobody had fully developed before. Graduate student Katie Booman, then at MIT, led development of one of the key imaging algorithms used to reconstruct a coherent picture from the sparse, incomplete data collected by a network of telescopes scattered unevenly around the globe, rather than a single continuous dish. To guard against any single team's assumptions accidentally biasing the final image, the collaboration split into 4 independent working groups, each processing the same raw data separately, without communicating results until they were ready to compare. All 4 groups converged on essentially the same glowing asymmetric ring. The team pointed their combined instrument at the supermassive black hole at the center of a galaxy called M87, 55 million light-years away, and separately at our own galaxy's Sagittarius A star. Processing the enormous volumes of collected data took nearly 2 years. On April 10, 2019, the Event Horizon Telescope collaboration finally released the result. A glowing, asymmetric ring of superheated matter and light, wrapped around a dark central shadow, the black hole's event horizon silhouetted directly against its own surrounding glow. It was, by any reasonable definition, an actual photograph, not an illustration, of an object John Michell had speculated might theoretically exist, all the way back in 1783. In 2022, the same collaboration released a second image, Sagittarius A star itself, the supermassive black hole at the very center of our own galaxy. The same object Genzel and Gies had already tracked so precisely through decades of stellar orbits. It's worth sitting with the full shape of this story for a moment, because it's genuinely unusual, even by the standards of the history of science. An idea speculated on paper in 1783, given real mathematical teeth by a soldier who died before seeing his own solution properly recognized, then aggressively suppressed by one of the most respected scientists of his era, publicly humiliating a 19-year-old who turned out to be correct, then set aside almost entirely for 2 decades by a field distracted by a world war, then slowly, painstakingly rebuilt piece by piece. A naming, an X-ray binary, a friendly wager, a radiation prediction that opened a paradox still unsolved, 3 decades of stellar tracking at the galaxy's core, a gravitational wave detection, and finally, an actual photograph, assembled from a telescope the size of the entire planet. A Chandrasekhar, humiliated in 1935 for correctly calculating exactly how a star could collapse into one of these objects, lived to see black holes go from a scientific punchline to one of the most actively studied objects in all of astrophysics. He died in 1995, 24 years before humanity finally took an actual picture of the thing he'd been mocked for describing correctly as a teenager. Eddington, for his part, never fully recanted his rejection of Chandrasekhar's work before his own death in 1944, and history has treated the episode as a genuine cautionary tale about the danger of letting institutional authority override careful mathematics, however uncomfortable the mathematics might seem at the time. It's also worth noticing how unevenly credit tends to travel through a story like this one. Schwarzschild's name survives attached to the very geometry of a black hole's boundary. Hawking's name survives attached to the radiation that might one day cause black holes to evaporate. Kerr's name survives attached to every rotating black hole solution used in modern astrophysics. Chandrasekhar's name survives attached to the mass limit that started the entire modern chapter of this story, but only after decades spent fighting for that same recognition against a far more powerful figure who was simply wrong. The event horizon itself remains, in a very real sense, the edge of what we can currently understand. Everything this video has described, the mathematics, the observations, the photograph, describes what happens right up to that boundary. The edge past which our current physics simply stops giving reliable answers. What happens inside it, at the singularity general relativity predicts but almost certainly doesn't correctly describe, remains one of the genuinely open frontiers of physics, waiting for whatever theory eventually manages to properly unite gravity with quantum mechanics. 236 years separate John Michell's speculative dark star from an actual photograph of one. Whatever finally resolves what's happening past that boundary may well take just as long to arrive. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.